Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we are doing a deep dive into Unit 11, and we're exploring the really revolutionary concept of the wave's nature of matter. Our mission is to make this topic simple, clear, and absolutely safe for your exams.
This is one of those topics that really bends your mind, isn't it? I mean, we hear about the dual nature of light all the time, but the idea that matter, things we can actually touch, also behaves like a wave that feels like it's straight out of science fiction.
It does, and that feeling is exactly where we'll start. Let's begin with a very simple everyday question. We all accept that light is both a wave and a particle. But what about us? If I walk through a doorway, I just walk through it. Why don't I diffract or show any kind of wave interference, like light does when it passes through a narrow slit?
Wait, hold on. Are you actually suggesting that I have a wavelength when I'm walking? That sounds impossible. I'm very clearly a solid particle with a certain mass and a certain velocity.
And that is the exact mystery that Louis de Broglie tackled almost 100 years ago. The thing is, the moment we shift from our big macroscopic world to the tiny subatomic world, the rules completely change. We know for a fact that high-speed electrons, which are definitely particles, behave just like waves in an electron microscope. They show clear diffraction patterns.
So what's the difference? Why do electrons show it and I don't?
It's all about the scale. When we actually calculate your personal de Broglie wavelength when you're just walking, the number we get is, well, it's almost meaninglessly small. The calculation gives us a wavelength of around 9.5 into 10 to the power of minus 36 meters.
10 to the power minus 36, that number is... It's just zero for all practical purposes. So
Yeah.
how can we even say that I have a wave property if it's that small?
But that's the genius of the idea. Because that wavelength is so incredibly small, it perfectly explains why classical mechanics, which treats you as only a particle, works so well in our everyday world. The wave effects are there, but they are completely undetectable. For subatomic particles, however, that tiny wavelength suddenly becomes very, very relevant. Okay, so let's unpack the core idea. Let's see what de Broglie was thinking. It all started with a very simple and elegant argument about symmetry in nature. Physicists had just discovered that light, which everyone thought was a wave, also has particle properties, photons. So de Broglie simply asked, why shouldn't it work the other way around?
That makes a lot of sense. If nature is symmetrical, then if a wave can be a particle.
Then a particle must also have some kind of wave property.
Exactly. That was his proposal in 1924. He said every moving particle, an electron, a car, even you, has a matter wave associated with it.
But was it just about symmetry? I mean, what big problem was this idea actually solving? Why did it become so important? That's a great question. It wasn't just a philosophical idea. It solved one of the biggest puzzles in physics at the time, the stability of the atom.
Ah, right. The classical problem where the electron should spiral into the nucleus.
Precisely. According to classical physics, an orbiting electron is an accelerating charge, so it must radiate energy. If it loses energy, its orbit shrinks, and boom, the atom should collapse in a fraction of a second. But they don't.
And we know they don't. So the classical idea was wrong somewhere.
The mistake was thinking of the electron as just a tiny ball orbiting a nucleus. De Broglie said, let's stop thinking of it as a planet. Instead, let's imagine it as a wave wrapped around the nucleus, like a vibrating guitar string.
Oh, a guitar string analogy. I like that. That immediately makes me think of specific notes or specific frequencies being allowed, not just anything.
You've got it. A guitar string can only vibrate in specific patterns, right?
Okay.
These are the standing waves. If you try to create a wave that doesn't sit perfectly, say 2.5 wavelengths, it just interferes with itself and dies out instantly.
So, for an electron's orbit to be stable, its wave must fit perfectly around the nucleus. It has to connect back on itself smoothly.
Exactly that. That is the condition. We visualize the electron not as a solid dot, but as a stable, fuzzy cloud, a standing wave pattern. Only those orbits where an integer number of wavelengths fit the circumference, where n times lambda equals 2 pi r, are allowed. Any other orbit is forbidden. And here's the most beautiful part. When you take this condition, not 2r, and you plug in the formula for the de Broglie wavelength, it mathematically derives Bohr's quantization rule for angular momentum.
No way. So Bohr just sort of guessed that rule to make his model work, but de Broglie actually explained why it has to be that way. It's just a natural consequence of the electron being a wave.
That was the breakthrough. It turned an arbitrary rule into a necessary consequence of wave mechanics. Quantization wasn't some strange new magic. It was just what waves do when they're confined to a small space.
Yeah.
Okay, so now that we have the deep conceptual picture, let's get ready for the exam. Let's look at how the insert textbook formally defines this relationship. Could you read out the definition for us?
Yes. The text says, the wavelength lambda associated with a particle of momentum p is given as lambda equals h over p, which equals h over mv.
Thank you. That simple formula, lambda equals h over p, is the famous de Broglie relation. Now, what's the first thing that strikes you when you look at that equation?
It's the two sides. On the left, you have lambda, which is wavelength, a pure wave property. And on the right, you have p, momentum, which is a pure particle property. They seem like opposites.
Excellent. And what connects them? It's Planck's constant h. It acts like a bridge between the particle world and the wave world. This duality is universal. It applies to everything. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. So let's go back to that paradox we started with. Why don't we see your wave nature? Let's use this formula and look at a simple numerical comparison. Let's compare a cricket ball to an electron.
Okay, this should make it clear.
Let's take a 150-gram cricket ball moving at 30 meters per second. Its momentum p is about 4.5 kilogram meters per second. Now, when we put this into de Broglie's relation, the wavelength we get is about 1.47 into 10 to the power of minus 34 meters.
Okay, there's that number again, minus 34. It's so small that no instrument could ever detect it. So for the ball, its wave nature is effectively non-existent.
You were absolutely right. It's there in theory, but impossible to measure. Now, let's look at an electron. Its mass is tiny, just 9.11 into 10 to the power of minus 31 kilograms, moving really fast. Its momentum is much, much smaller, around 4.92 into 10 to the power of minus 24. Wow. Now, when we calculate its wavelength, we get a value of 0.135 nanometers.
0.135 nanometers. Now, that sounds small, but it's a huge number compared to minus 34. Is that wavelength significant in some way?
It is hugely significant. That wavelength is in the same range as the spacing between atoms in a crystal. This means if you shoot a beam of these electrons at a crystal, the gaps between the atoms will act like a diffraction grating for the electron waves.
And if it's a wave going through a grating, it should create an interference pattern, just like X-rays do.
That is the ultimate proof. And this experiment was actually done by Davison and Germer. They fired electrons at a nickel crystal and saw a clear diffraction pattern. It was undeniable proof that particles of matter also behave like waves. And this idea that particles are waves described by a wave function is what leads us directly into the next chapters on atomic structure and the full theory of quantum mechanics. Now, before we summarize, let's talk about a few silent killers. These are common misconceptions that can cost you marks in the exam.
Yes, please. These are the most important things to know.
Okay, silent killer number one. Many students think Planck's constant h is just a mathematical conversion factor. This is the wrong idea. The correct idea is that h is a fundamental constant of nature. Its specific tiny value is what sets the scale for everything. It defines the boundary where the world stops being classical and starts being quantum.
Oh, I see. So h isn't just a random number in a formula. Its value is the reason the quantum world is so different from our world. If h was 0, everything would be classical.
Precisely. Now, silent killer number two. The wrong idea is that this wave-particle duality thing only applies to light, and that matter is just particles. The correct idea is that this duality is universal. De Broglie showed that everything, light and matter, has both wave and particle aspects.
So it's about complementarity, not a choice. It's not that an electron is sometimes a wave and sometimes a particle. It's always both.
Exactly. The experiment you perform decides which aspect you see. Okay, third killer. This relates to the photoelectric effect. The wrong idea is that all ejected electrons have the same kinetic energy, the Kmax. Students memorize the formula Kmax equals high minus W and apply it to every electron.
But that doesn't make sense. If an electron comes from deeper inside the metal, it must lose some energy on its way out, right?
Exactly. The correct idea is that Kmax is only for the electrons on the absolute surface that escape without any collisions. Most electrons lose some energy, so you get a whole distribution of kinetic energies from 0 all the way up to that maximum value. All right, to lock all of this in your memory, let's use a few quick anchors. First, just remember the two key equations linked by HE equals high for light and equals HP for matter, energy and wavelength. And here's a catchy phrase. Frequency funds the escape. Momentum defines the wave. It reminds you that frequency gives the photon energy to free an electron, while the particle's momentum sets its wavelength.
Frequency funds the escape. Momentum defines the wave. I like that. It connects the two big ideas. What about a physical gesture?
Yes. To remember the standing wave condition, Hold your hands out to form a circle. That's the orbit. Now with your other hand, trace a wave going around that circle. The key is that the wave must connect back to its starting point smoothly, with no break. If it doesn't close perfectly, it's not a whole number of wavelengths, and that orbit is forbidden. It self-destructs. Okay, to finish our deep dive, here are the 3 essential exam-safe points about the wave nature of matter. 1. Broglie proposed that all moving matter has a wave property. The wavelength is given by lambda equals h over p, directly linking the wave concept of lambda to the particle concept of p2. These matter wave effects are only observable for microscopic particles, like electrons. That's because their tiny mass gives them a large enough wavelength to be measured, something comparable to the size of atoms. And 3. Wave-particle duality is universal. It's not a contradiction. It's a fundamental complementarity of reality. Neither the wave picture alone nor the particle picture alone is ever complete. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is Prof Sam Light.
Yes, ProfSam.com. Thank you for diving deep with us today.